Somewhere online right now, there's a video insisting that Google researchers were running tests on a quantum chip, watched something appear inside a superposition that shouldn't have been there, and simply stopped, refusing to continue the experiment. It's a great, spine-tingling premise. It's also, and I want to say this plainly before we go one sentence further, not something that happened. There's no research paper behind it, no named lab, no scientist quoted on the record, nothing but a cluster of nearly identical videos recycling the same vague, unsourced claim. In fact, this exact genre of video has already been called out and debunked by people who actually looked into it, because it follows a template that's shown up again and again around Google's quantum chips going back years. Always the same shape. Something mysterious happened. Scientists were alarmed. Nobody can say exactly what, or where, or when. But here's why this is worth a real, honest 15 minutes of your time anyway. The phrase at the center of this fake story, something showed up in the superposition, touches on one of the strangest, most genuinely debated concepts in all of physics. And once you understand what superposition actually is, you'll see exactly why this specific claim couldn't be true, even in principle, not because Google is hiding something, but because of how superposition itself works. And once we've cleared that up, I want to walk you through what Google's quantum chips have actually verifiably done, because the real story turns out to be plenty strange enough without any invented scares attached to it. Let's start with superposition itself, because it's one of those physics terms that gets thrown around constantly without much explanation of what it actually means. In classical, everyday physics, an object has a definite state at all times. A coin is either heads or tails even before you look at it. A light switch is either on or off. Quantum mechanics works differently, in a way that still unsettles people even after a century of getting used to it. A quantum particle, like an electron or a photon, or a qubit inside a quantum computer, can exist in a superposition, meaning it holds multiple possible states simultaneously, not as a hidden fact we simply haven't discovered yet, but as a genuine, verified feature of how the particle actually behaves, right up until the moment someone measures it. A qubit in superposition isn't secretly a 0, or secretly a 1 waiting to be revealed. It's genuinely, physically, both at once, described by a mathematical wave function that captures the exact proportions of each possibility. Here's the part that makes the entire premise of something showed up inside a superposition a contradiction in terms, rather than a spooky discovery. The act of measuring a quantum system is precisely the thing that ends at superposition. This is one of the most well-established, thoroughly tested principles in all of quantum mechanics, and it goes by a specific name, wave function collapse. The moment you observe, measure, or in any way extract definite information from a qubit in superposition, that superposition doesn't persist alongside your observation. It collapses into one single definite outcome, 0 or 1, and the multiple state nature of the superposition is gone the instant you look. You cannot peer inside an ongoing superposition and see some third thing lurking there while the superposition continues undisturbed, because the very act of peering is what destroys the superposition in the first place. It's a little like asking what a coin looks like mid-flip if you could freeze time and look really closely without the coin landing. Except in the quantum case, physics itself forbids that kind of freeze frame peak. The observation and the collapse are the same event, not two separate steps you could pull apart and examine independently. So a story about researchers seeing something appear inside a superposition while the superposition kept going undisturbed isn't describing an unusually rare or classified event. It's describing something the core, well-tested mathematics of quantum mechanics says cannot happen, the same way you can't design a video camera that films the far side of a mirror. This is exactly the kind of detail that separates a genuinely unsettling scientific finding from an urban legend dressed up in scientific language. Real quantum experiments deal with superposition constantly, and physicists have very precise, well-established language for describing what happens when a superposition ends, and it's never described as something appearing inside it. It's described as measurement, or collapse, or decoherence, terms with exact mathematical definitions, not the vague, ominous phrasing that shows up in a video built to generate views, rather than to accurately describe an experiment. Now, since we've cleared the myth out of the way, let's talk about what Google's quantum chips have actually verifiably done, because the honest version of this story doesn't need any invented scares to be genuinely fascinating. Google's quantum computing program has produced a real, well-documented string of achievements over the past several years, starting with its Sycamore processor back in 2019, which the company claimed had achieved quantum supremacy, completing a specifically designed benchmark calculation in about 3 minutes and 20 seconds that Google estimated would take the world's fastest classical supercomputer roughly 10,000 years to match. That claim was, appropriately, met with real scientific pushback almost immediately. IBM researchers challenged it directly, arguing that a properly optimized classical supercomputer, using more sophisticated simulation techniques, could actually complete the same task in about 2.5 days rather than 10,000 years, a dramatically smaller gap than Google's original estimate. That back and forth is worth remembering because it's exactly the kind of real scientific disagreement that legitimate breakthroughs generate. Researchers checking each other's math, challenging assumptions, and narrowing claims through actual technical argument, a world apart from a vague, unsourced video claiming researchers were too spooked to continue. Google's newer chip, Willow, unveiled in December of 2024, pushed the same basic idea further and did so with considerably more rigor built in to address exactly the kind of skepticism the earlier Sycamore claim had faced. Willow demonstrated a real, independently significant achievement in quantum error correction, showing that as researchers added more physical qubits to a properly designed error-correcting code, the logical error rate actually dropped exponentially rather than getting worse, a milestone quantum computing researchers had been chasing for roughly 3 decades because it suggested, for the first time with solid experimental backing, that building larger, more reliable quantum computers was a genuine engineering path forward rather than a fundamentally losing battle against accumulating errors. On top of that, Willow completed a specific benchmark computation in under 5 minutes that Google estimated would take a classical supercomputer an almost incomprehensible 10 septillion years, a number so large it exceeds every known timescale in physics, including the age of the universe itself many times over. It was in that same announcement that Google's Hartmut Nevin made the comment that's fueled a whole separate wave of viral claims, writing that Willow's performance lends credence to the notion that quantum computation occurs in many parallel universes, referencing physicist David Deutsch's many worlds interpretation of quantum mechanics. That statement is real, it's genuinely controversial among physicists, and it's worth understanding on its own terms because it shows you what an actual, legitimate scientific controversy around Google's quantum chips looks like, as opposed to the fabricated something appeared and scientists fled genre. Deutsch's argument, dating back to his 1997 book, The Fabric of Reality, proposes that quantum computers derive their remarkable power by performing calculations across countless parallel branching universes simultaneously, with the different branches interfering with each other to amplify correct answers and cancel out incorrect ones. Plenty of serious physicists pushed back on Nevin's framing, pointing out that the more mainstream Copenhagen interpretation of quantum mechanics explains exactly the same mathematics, exactly the same interference effects, without needing to invoke any parallel universes at all, treating quantum superposition as a description of probability within a single universe rather than a claim about physically real branching realities. Both interpretations predict the exact same measurable outcome from Willow's experiment, which is precisely why physicists say this remains an open interpretive question, rather than something Willow's performance could settle one way or the other. That's a real, sourced, ongoing scientific debate, expressed by a named scientist in an official company announcement, and it's a great example of how strange and genuinely debatable real quantum computing findings can be, without anyone needing to invent a story about researchers refusing to continue an experiment. There's also a genuinely fascinating, fully real experiment from Google's quantum computing team that gets far less viral attention than it probably deserves, precisely because it doesn't need any embellishment to be remarkable on its own. In October of 2025, a team using the Willow chip ran an experiment called Quantum Echoes, designed to measure something called an out-of-time order correlator, essentially a way of tracking how a tiny, deliberate disturbance introduced into a scrambled, chaotic quantum system can be traced all the way through that chaos and recovered afterward, like sending a whisper into a hurricane and picking out its echo on the other side. This measurement connects directly to some of the deepest open questions in theoretical physics, including how information behaves inside black holes and how quantum randomness, in the earliest moments after the Big Bang, may have seeded the large-scale structure of the universe we see today. That's a real, peer-reviewed, published result, involving actual physics that legitimately touches on some of the biggest questions humanity has ever asked, and it required absolutely no invented mystery about superpositions hiding something spooky, because the real science was already strange enough to earn genuine, serious attention on its own honest merits. So why does this particular genre of fabricated story, scientists refuse to continue, keep showing up around quantum computing specifically, recycled again and again with slightly different wording? I think it's worth understanding the pattern, honestly, because it'll help you spot the next one before you fall for it. Quantum mechanics already sounds deeply strange to most people encountering it for the first time. Particles existing in multiple states at once, measurement changing outcomes, entanglement linking particles across any distance instantaneously. That genuine strangeness makes quantum computing an unusually fertile ground for this kind of manufactured mystery, because the real science is already weird enough that an invented embellishment doesn't feel obviously implausible to someone without a physics background. Add in a recognizable, credible-sounding company name like Google, a dramatic but vague claim that avoids any specific checkable detail, no named researcher, no paper, no date, no location, and a title built entirely around triggering curiosity and unease, refused to continue. Something appeared, and you have a formula that's been used across dozens of nearly identical videos, not just about quantum chips, but about AI chatbots answering existential questions, about physicists supposedly quitting their jobs after a discovery, about all sorts of vague, unfalsifiable claims dressed up as breaking science news. The tell, every single time, is the same. Real scientific claims, even genuinely strange ones like Nevin's multiverse comment or the quantum echo's black hole connection, come with names, dates, publications, and specific checkable details, because that's how science actually works. Through claims, other scientists can examine, challenge, and either replicate or debunk. A claim that can't be traced to any of that, no matter how many videos repeat it with slightly different words, isn't a suppressed secret, it's just a story with no evidence behind it, dressed up to look like one. So here's the honest, complete version of what you were actually looking for when you clicked on this headline. Nobody saw something impossible appear inside a quantum superposition, because the physics of superposition makes that specific kind of observation a contradiction. The measurement that would let you see anything at all is the exact same event that ends the superposition you'd be trying to peek inside of. But Google's real quantum computing program has produced a genuine, well-documented string of strange, boundary-pushing results, a supremacy claim that sparked a real and healthy scientific fight with IBM, an error correction milestone that quietly solved a 3-decade-old engineering problem, a comment about parallel universes that reignited a 70-year-old philosophical debate among serious physicists, and an experiment that gave researchers their first real controlled window into the kind of information-scrambling physics believed to govern black holes in the earliest moments of the universe. That's the real story. It didn't need an invented scare to be worth 15 minutes of your attention, and now that you understand both the fake version and the real one, you're in a considerably better position than most people, scrolling past that same recycled thumbnail to actually tell the difference the next time a headline like this one shows up in your feed. Let's dig a little deeper into why physicists are so confident that measurement destroys superposition. Because it isn't just a rule someone made up to sound authoritative, it's one of the most repeatedly, rigorously tested principles in the entire history of experimental physics. The classic illustration, the one nearly every physics student encounters early on, is the double-slit experiment. Fire individual particles, electrons or photons, one at a time, at a barrier with 2 narrow slits cut into it, and let them land on a screen behind it. If you don't try to detect which slit each particle passes through, the particles build up an interference pattern on the screen over time, alternating bands of high and low density, exactly the kind of pattern you'd expect from overlapping waves, strong evidence that each individual particle is, in some real sense, passing through both slits simultaneously and interfering with itself, a direct signature of superposition in action. But the moment you place a detector at the slits specifically to measure which slit each particle actually goes through, the interference pattern vanishes completely, replaced by 2 simple clumps directly behind each slit. Exactly what you'd expect from ordinary particles traveling through one slit or the other, not both. The particles behave differently depending on whether they're being measured, and that difference has been reproduced in laboratories worldwide with different particles, different setups, and different detection methods for the better part of a century. This is precisely why physicists treat wave function collapse as a foundational, extraordinarily well-supported feature of quantum mechanics, rather than a debatable or poorly understood detail. And it's exactly why the premise of observing something inside an undisturbed superposition runs directly against one of the most thoroughly tested results in all of experimental science. It's worth being fair, too, about where genuine scientific uncertainty in this area actually does exist, because there is real, serious debate in physics about superposition, just not the kind this fabricated video is trying to sell you. The genuinely open question isn't whether measurement ends superposition. That part is settled and uncontroversial. The open question is why it happens, what physically constitutes a measurement in the deepest sense, and what that collapse actually implies about the underlying nature of reality, which is exactly the territory the Copenhagen versus many worlds debate we covered earlier occupies. Some physicists, working on a related but distinct research program called quantum decoherence theory, have developed increasingly detailed mathematical models describing how a quantum system's fragile superposition gradually leaks away through unavoidable interactions with its surrounding environment, essentially explaining collapse as an extremely fast, practically irreversible spreading of quantum information into an enormous number of environmental degrees of freedom, rather than a single instantaneous event. That's a real, active, technically rich area of physics research, and it's a considerably more interesting rabbit hole to fall down than any fabricated video claiming researchers panicked and shut down a lab. There's also something worth saying honestly about why these fabricated scientists were shocked and refused to continue. Videos keep finding an audience despite having no substance behind them, because understanding the appeal isn't the same as excusing the deception. Real science, especially in a field as technically dense as quantum computing, often moves slowly, communicates in careful, hedged, heavily caveated language, and delivers its most exciting results wrapped in enough technical qualification that the genuine strangeness can get lost on a general audience. A video that skips all of that and instead promises a single dramatic moment, scientists gasping, an experiment abruptly halted, something inexplicable caught on camera, is simply easier to consume and easier to feel something about, even though it isn't true. That's not a flaw unique to quantum computing content either. The same basic template, vague mystery, invented urgency, a stunned but unnamed group of experts, shows up constantly across pseudoscience and conspiracy content more broadly, whether the topic is ancient history, medicine, or artificial intelligence. Recognizing the shape of the template is genuinely useful well beyond this one specific video, because the next one, whatever subject it latches onto, will very likely follow the exact same structure. If there's a genuinely useful habit to take away from all of this, it's a simple one. When a claim about a scientific breakthrough or a scientific scare comes without a name, a date, a paper, or an institution attached to it, treat that absence itself as the most important piece of information in the story, more important than anything the video actually claims happened. Real quantum computing news, even the strangest and most genuinely debated parts of it, like Nevin's multiverse comment or the ongoing dispute between Google and IBM over supremacy claims, always comes with exactly those details, because that's simply how legitimate science gets reported and checked. The fabricated version never does, and once you know to look for that gap, these videos become a lot easier to spot and a lot less unsettling. The next time one shows up promising that scientists have seen something they refuse to talk about.